good to go? All right. Good afternoon to everybody. And congratulations to everybody who made it through the whole day that started with us this morning. Way to go. Those of you that have joined us more recently, my name is John Bean. I co-lead the immersion project with Rolf. My day job, though, is with Green Revolution, and I'll be wearing my GRC hat today versus my OCP. So I'm going to have a conversation a little bit different than some of the other ones here with targeted flow, direct flows, etc. So Andy from Lubrizol made a comment earlier today that I do agree with, and that is that the runway for buoyancy, natural convection, is still a pretty long runway. We have room to grow and move there. There's no doubt about that. But with that said, we know that the roadmaps of various suppliers out there are going to push us into the need for targeted flow, forced flow, whatever you want to call it. And that may also be to enable heat reuse that was spoken to by Casey. So there's a number of reasons that we might want to go down that path, and well, we will have to go down that path. But as we introduce this new technology, it has implications to the balance of the system, okay? So the CDU, the rack, they have to be able to work with this technology in a very efficient and predictable way. So what I'm going to talk about here today is iDLC. It's immersion direct liquid cooling. And this is really more about the ecosystem that's going to support the technology. And I'm going to speak specifically to just one topic, and this is a technique of many that may help improve the efficiencies of this kind of technology as we deploy it, okay? So you've seen this diagram, and I really appreciate Casey and others that have got it up there and exposed to you all. You're familiar with the curve on the efficiency heat sink. Casey was sharing with you, hey, once you go from about down to about 2 liters per minute with the efficiency heat sink, you don't see a lot of improvement anymore. But certainly with the performance one, it's more like about 4 liters per minute. So the performance one, you're still getting some meaningful improvements of the heat transfer coefficients all the way out to 4 liters per minute before that starts tapering off. Now, he mentioned to you that, you know, we have the 2 different flow paths, and we've got the targeted flow, and then we've got the normal flow going into the bottom of the tank, and they're converging and coming back together, and they're all going through the CDU, and they're all going through every element of the CDU. So if you look at this very simple diagram over on the right-hand side, you can see that we have a whole bunch of parallel flows between all the different heat sinks and the normal bulk flow through the tank. They all get summed together and pushed into the pump, pushed through the filter, and the filter could be on the other side of the pump. I'm not going to really get hung up on that. But then they're all stuffed through the heat exchanger. And we know from our work in this industry that the heat exchanger represents a fairly substantial portion of the pressure drop through the system. There may be cases where we might want to bypass some of that flow around that heat exchanger. It may not make sense in all cases to take the pressure hit of the heat exchanger by forcing every bit of the dielectric fluid through it. So here we're introducing an element of a motorized control bypass valve that, depending on what's going on with the system, it may be able to, you know, bypass some portion of the total flow around that heat exchanger, lowering the flow rate, lowering the pressure drop, and lowering pumping power. So this study is not on any specific product, okay? So this is being evaluated using a tool from Alpha Laval that we can predict the performance of a heat exchanger. We can calculate, you know, what the pressure drops will be, what the flow rates and temperatures will be, and because we're bypassing that heat exchanger, some of that fluid isn't being cooled, okay? What bypasses the heat exchanger doesn't get cooled. But it does reconverge with the heat exchanger fluid that was cooled, and we need to worry about the mixed fluid temperature in this case. So a simple little equation here over on the right-hand side that shows how we get the mixed temperature, and ultimately that mixed temperature of what was cooled, what wasn't cooled, is what the heat sinks are seeing and what's going back into the tank. So we really need to understand the implications of bypassing fluid and what that does to the actual fluid temperature going to the heat sinks, going into the tank. So with this study, we had some fixed values. So we're going to lock down the target capacity on the various scenarios, the water inlet temperature, and the dielectric flow rate. But we allowed ourselves a few levers to play with. Obviously, one lever is how much flow are we going to bypass? What would be the water flow rate to be able to meet the temperature requirements, and then the return dielectric temperature. So we do have a few levers that we're allowing to move around in this technology. So looking at a number of different scenarios here, this first one is looking at a 50U rack, and when I say 50U, I mean it has 50U available for IT equipment, and we're going on the assumption that every U can support up to 4 sockets. And we're seeing today that with these performance heat sinks, 1,000 watts is no problem whatsoever. So we said, okay, well, 4 sockets per U gives us a total of 200 sockets at 2.5 liters per minute. You know, that's talking 500 liters per minute right there for the heat sinks. Then the tank would have another 200 liters per minute. So you're talking a total of 700 liters per minute that's being circulated. And you know, all of that is being pushed through every element of the CDU, including the heat exchanger. So the table on the bottom is kind of looking like, okay, as we start bypassing some of this flow, what happens to the system? Is there a value proposition there? So we divide this table in the bottom up into 3 groupings. We have the dielectric fluid over on the left-hand side. We have the water in the center. And then we kind of have the mixed stuff going on over on the right-hand side. So for both fluids, we're looking at the inlet and outlet temperature. We're looking at the flow rate. We're looking at the pressure drop associated with pushing that fluid through the heat exchanger. Now I want to stress that this study is looking at the heat exchanger only. There's other pressure drops in the system, but this is looking about what we can do if we shuffle fluid around the heat exchanger rather than stuffing it all right through it. So then on the water side, similarly to the dielectric, we're looking at water in, water out, flow rate, the pressure drop, and then we have this product of a couple of different numbers there where we have the pressure drop, volumetric flow rate, and the specific gravity. So we're taking the product of all those numbers, and then later on we're using that to calculate the water power that is required to do that amount of work through the heat exchanger. So as we push the fluid through the heat exchanger, we're doing work. And then we're summing up the 2 fluids and the work associated with them over in the second to the far right column. That's HX fluid power in watts. So the study is looking at, as I mentioned, bypassing. So the top row is at the full flow. That's no bypass around it. Then each of the subsequent rows, we're bypassing 10%, 10% more, and 10% more. So we're basically opening the bypass valve further and further, bypassing more and more fluid. And what you can see is 2 things are interesting here. Is you can see on the fluid power, we start dropping the fluid power, and it's not quite so interesting here. We're going down just a little bit in this scenario from 581 to 540 to 534, and then we're jumping to 744. What's happening and why we're jumping is we got to push so much water through the heat exchanger at some point that we're taking on all kinds of fluid power on the water side, even though we're saving it on the dielectric. And the reason we're pushing all that extra water flow is to close up the approach temperatures so that that mixed temperature is still where we'd want it to be. So in this scenario, the gains are fairly minimal. But, okay, there's more to the story. You got to evaluate, you know, quite a few different data points. Let's see, did that advance? Yeah. So this is another scenario where we said, okay, let's look at this thing not at 100% load. Let's throttle it back to just 80% load. Okay, so now the CPUs or GPUs are running 800 watts. The flow rates have been scaled back proportionately. And here we're looking again at the same study. The full flow is at the 33.6. And here you can see we're going from 382 down to 317 watts. Not a big delta, but a meaningful percentage for sure. So this is an interesting percentage, okay? So it's getting to where, yeah, maybe in absolute values, not so cool, but meaningful percentage. But now let's push this thing a little bit further out. And here's where things start to say, well, you know what? There may be something here. And we've done a whole lot of different scenarios here, and I could show you some that are even more optimistic and some that are worse. So I kind of took like the lower 30% up to the upper 80th percentile of performance improvements. So here you can see that as we're beginning to do this bypass scheme, we're going from 982 watts down to 647. So we're shaving off over 300 and some watts by bypassing the fluid flow. We're still able to get to a mixed temperature very close to the original target, and we let that float around a little bit, as I mentioned. We're not locking it down, but we did let that float around a little bit. But you can see in this application, depending on what you're trying to do and your operating duty point, there may be some value proposition to try and manage some of the flows through the CDU, whether it be around the heat exchanger, bypass filters, all kinds of schemes may come to play. But what we're focused on here is just looking at the heat exchanger and what we can do to improve that performance. I think this chart kind of summarizes it a lot more clearly and lets you get a little bit better picture of what's going on. So we have the three different scenarios on the chart over here on the right-hand side. And if you look at the right side of each one of those curves, the far right side is 100% flow through the heat exchanger, and the y-axis is the fluid power between the dielectric fluid and the water. So as we start bypassing, you can see in all cases that fluid power starts coming down, coming down, coming down as we bypass more and more. And then at a certain point it says, oh boy, I'm doing so much more work now on the water side that I've lost my advantage now. So the point here is that there is a optimal point, and it's not just like you could set a valve, walk away, and forget about it like you're done. So the system would have to have some intelligence and some dynamic capability to manage this. And you know, here the savings are in percentage of reduction. So you can see you're cutting the pumping power by 1/3 on that more advantageous scenario for this kind of technology. So in summary, what can we take away from this? The iDLC directed flow heat sinks definitely in aggregate have more flow moving through the CDU than the normal tanks we're used to, okay? And whenever we have more of something, we need to be a little bit more vigilant of how we manage it. So we kind of need to keep an eye on this, these increased flow rates, seeing what we can do to mitigate and give the best efficiency possible. So the flow management technique that we discussed here, it shows some advantage for system tuning to get to a point of best efficiency. But due to the dynamics of it, it's very likely that any technique like this would want to have some real-time control capability where we can modulate this and monitor it and make sure that we're doing the right thing at every moment in time. Then obviously the call to action. Always have to have a call to action with these slide decks. So the problem to solve is back to the point with these directed flow technologies, the increased flow rates, we do need to pay more attention and do our due diligence to make sure that we're optimizing the efficiency of the balance of the system, okay? So it's not just about the heat sinks, it's about the balance of the system. How might you get involved with this? So we've had a lot of conversations here over the last several hours about the various work streams in the immersion project. I think one of those work streams that we might want to take a look at would be the requirements document. And I think the requirements document right now, well, I don't think, I know, it doesn't really comprehend a system that is thinking about targeted flow. So as we're going to see this being more prevalent in the industry, I think it's logical that within the requirements document, we might want to say, hey, what does this mean to us? And we need to start thinking about some ways to get on a common footing so vendors are approaching their numbers that they share with the customers in the similar way that they're not confusing the industry on how they report their data at a minimum, okay? Then I also think the heat sink design. Intel's done a great job with their heat sink design. My hat's off to them. Their efficiency heat sink, wonderful that they're contributing that as open source. Their performance one, it's pretty impressive where they've gotten that. But for sure, we're not at the end state there. And I think Casey and everybody from Intel would say, hey, yeah, we've got in our mind's eye things that we can do to improve that. I think the industry needs to continue to push these heat sinks for optimal efficiency while minimizing pressure drops. So there's work to be done there as well. So the other thing is, you know, you could go check out the immersion requirement document. I'd like to refer you to the link there in GRC's iDLC white paper as well. So I did give myself a few minutes for questions. Throw a little mud at me or whatever, and we'll take it from there, okay? So any questions from anybody? Late in the day. Well, all right, then maybe I'll yield back and we can have a little bit of a earlier start on the final guy and get us all out of here a bit earlier then, okay?